Hi class, so this section we are looking at using equilibrium constants, chapter 10.4. So the last section we learned how to calculate the equilibrium constants, but nothing else was said about what those values mean. Now we're going to look at those values and actually look into what their values mean about that chemical reaction and the equilibrium. So let me get started here. The values of the equilibrium constant, which is Kc, can be large or small, depending on whether the equilibrium has reached with more products than reactants or more reactants than products. So remember, when an equilibrium reaction occurs, whatever the concentrations are on the reactant side and on the product side locks in. They're not always equal, and in most cases they're never equal. They're actually very unbalanced, where one side has way more concentration of whatever that is than the other. So that's what the values actually mean. It tells you if you're looking at an equilibrium that produced more products, or actually has more reaction, the concentration of reactions in it. Reactant. So let's take a look at this one. This picture is from this page, and I'm going to break it down what exactly is going on here. So when we look at an equilibrium with a large equilibrium value, that means that the reaction has, when it hit equilibrium, had large amounts of products that were produced before the equilibrium and from the forward reaction when it hit equilibrium. So the equilibrium here, if we take a look at this reaction of sulfur dioxide and oxygen, which produces sulfur trioxide. When it hit equilibrium, it actually, so you see initially we have reactants, but there's no products because the reaction hasn't started. But the minute it started, and then when eventually it hit equilibrium, when equilibrium occurred, we actually had a very large amount of concentration of product and very small amount of reactant when this occurred. So when we fill in an equilibrium constant, we're going to have a larger number here. For remember, we're looking at concentration. So this is molarities. We're going to have a larger concentration number here and a smaller concentration value here. Then we can determine what our equilibrium is. And this is a larger number. And I'll show you why this is a larger number when we start looking at these. Okay, so let's take a look here. Now, an equilibrium with a small equilibrium constant means that when equilibrium occurred in the mixture, there was a very small amount of product and a very high concentration of a small concentration of products and a very high concentration of reactants. So let's take a look at this problem here. So we have nitrogen and oxygen, and it produces nitrogen oxide. At equilibrium, the reaction mixture contains mostly reactants and free products. How do I know that? Because I can look at this number and instantly tell you that this has a very small equilibrium value, and it contains very small amount of products, a concentration of products, and it contains mostly concentration of reactants. So let's take a look at this one. So initially we have a very high amount of concentration of our reactants, but as the reaction goes and then eventually hits equilibrium, we still have a very high amount of concentration of reactants and a small amount of a concentration of a product. It's not as high. You can see that some of it had to go in order to produce this. However, the small equilibrium constant means that it contains a very large amount of a concentration of reactant. How do I know that? Well, let's take a look at this here. So if you use 1 as your middle, the border, if your equilibrium constant is 1 or close to 1, that means that you have approximately equal concentrations of reactants and an equal concentration of products. However, if you think of this as being small equilibrium constants as below 1, this will tell you that you have most of reactants. So you have more reactants, a concentration of reactants, than you have of products. Now, if you think of above 1, you have mostly a concentration of products. So very small amount of concentration of reactants and more products. So if you think of 1 and then you start looking at values that are below 1 and larger than 1, how do you do that? Well, if you have values that have exponents in scientific notation that are negative, then that means that those values are less than 1. But if you have exponents in scientific notation that have more than, that are positive values with no negatives at the exponents, they are larger than 1. And this is, if you start looking at it, you'll generally start seeing this trend. So at equilibrium, a reaction with a large equilibrium constant contains mostly products, and an equilibrium constant with a small value contains mostly reactants. Here's a chart, and this will allow you to see, and I put a box so you can figure out how to read these. So we have the chart from the previous page, and we start looking at the values. This is a positive number, which means that if you write this out, it's not below 1, so it's mostly product. Positive exponent. Here's another one. Has a positive exponent, which means when you fill this out, write this out, it's above 1, so it's mostly product. When equilibrium mixture, when the equilibrium reaction occurs. Here is another one above 1, so it's mostly product. But now we have an exponent that's negative 2. If you write this out, this decimal is going to be moved out. It's less than 1. It's mostly reactant. And here we have another negative number that if you write this out, it's going to have, put a decimal and then move it over. It's going to have a lot of zeros below in front of this. This is mostly reactants. So this is not a difficult way. You just have to remember what the trend is that will help you understand when you're looking at a value what it means. So let's do some exercises here. So for each equilibrium constant, indicate whether the reaction mixture at equilibrium contains mostly reactants or products. So based on what I told you on the previous page here in this box, we're looking at this value. It is a positive number. So this is a number that's well over 1. So this is going to be mostly products. Here we have a negative number, which means that we're going to have mostly reactants. So reactants are favored at equilibrium for this one with the equilibrium constant, and products are favored at equilibrium for this equilibrium constant, and it's a large constant. Okay, so when we know the numerical value of the equilibrium constant and all the equilibrium concentrations, except for one is missing, we can actually calculate for the unknown concentration. So basically we're solving for x. That's it. We have all the other variables, we've got to move things around, and we're going to solve for x. For the reaction of carbon dioxide and hydrogen, the equilibrium concentrations are 0.25 molar for CO2, 0.80 molar for hydrogen, and 0.50 molar for water. What is the equilibrium concentration for CO? So we're given the balanced equation, and so let's take a look at what we have here. We have our concentration for CO2, we have our concentration for hydrogen, so that means we have our concentrations for the reactants. We have our concentration for water. So we're missing one of the concentrations for the products. And we're also given the equilibrium constant. So we know what we have, what we need our expression value, and we're going to use the balanced equation to set this up. So now we set it up as we have in the past. These are all 1 to 1 to 1 to 1 ratios, so we don't have any exponents for the coefficients. And now it's just down to simple, it's algebra. You just solve for the one that you don't have. So isolate the one that you need to separate from the rest so you can determine what the value is, which is done here. And now plug in all our values. And when you do, we can determine that the concentration for CO is 0.044 molar. All right, here's another one. At equilibrium, the reaction has concentrations, and it's giving us, when it shows it like this with the concentration and the compound inside and it's equal, this means that both of these concentrations are this molarity. So you don't have to write them out twice saying this is this molarity, and this is this molarity. You can put equal signs and it shows that these are both equal to that. So what is the concentration of our reactant at the beginning? So we are given both the polarities concentrations for the products, but we don't have the reactant. So again, we're given everything that we need, and now we just have to plug it in. So here we set up our equilibrium constant. Products are on top, reactants on the bottom, all the coefficients are 1, and then we solve for the one value of the concentration that's missing. We look at that, and now we plug in everything. So remember the equal signs? This means exactly that. They're both the same concentration, even though they're different compounds. We have our equilibrium constant, and the concentration of phosphorus pentachloride is 0.24 molar. And that's it.